Just what the heck is a morphing filter anyway? I'm Professor Fiore, and I'll explain it to you right now. All right, so the morphing filter is just a name I gave to kind of a different filter, something I haven't seen. What's the deal? Well, with a single knob, you can have this filter go from a low-pass filter into a notch into a high-pass filter. So you can just sweep this thing around. Now you might ask, why would I want to do this? Well, you know, for normal kinds of instrumentation, there probably isn't a great demand for such a thing. However, if you're a musician, well, you know, whatever floats your boat, right? It might be fun to plug your instrument into this filter and then play, have a go with it. Now, here's the deal. You're going to be able to use two things. A foot pedal, you know, like you would with a wah-wah or a phaser or something like that, and an LFO, right, a low-frequency oscillator. So you could kind of combine these things together. Now, basically, to really get a deep understanding of what's going on here, if you want to sort of design your own variation on this, there's a bunch of videos I did right before this in the Op Amps playlist in the active filter section that cover some of this stuff specifically. And I'm talking about state variable filter number 1 and also the series on voltage controlled filters, which utilize the state variable filter. So there's a handful of those. You probably want to take a look at those if you really want to dive down into here, truly get a deep understanding of what's going on, and then making your own variation on the theme. But I'm just going to give you an overview of what's happening. Basically, what we have here is a standard 4 op amp state variable filter. And a state variable filter is comprised of a summing amplifier and a pair of integrators, right? Each integrator is an op amp with a resistor and a capacitor. And there's 3 outputs, right? There's a high pass output, a band pass output, and a low pass output. There's 2 reactive elements, so this is ultimately second order, right? When we look at high pass and low pass, and then the band pass is like first order each side, so to speak. In other words, the roll-off rates would be 6 dB per octave ultimately, whereas they would be 12 dB per octave for the high pass and low pass outputs. And normally that's how we would use, you know, the state variable filter, right? We have these 3 outputs, whichever one we need, that's what we're going to tap off. And, you know, if we really wanted to, we could have a little switch to go between the 3. I'm not talking about a switch here. I'm talking about a continuously adjustable, you know, potentiometer that's going to morph, hence the name, between low pass, notch, and high pass. All right, now, just a real quick rundown here. The critical frequency is going to be set by this capacitor-resistor combo, and these 2 are going to be the same as these 2 for the integrators. It's basically a 1 over 2 pi RC kind of thing. So this, you're going to have 1 over 2 pi times 10 nano times 10K, you know, which is going to get you like 100 mics. You divide that, you know, take 1 over 2 times that, and you're going to end up with around 1.6 kilohertz. All right. So that's where this thing is going to resonate. That's the corner for the high pass and low pass. That's the center for the band pass. And then we have a little bit of this band pass output going over here into this 4th op amp, which is going to set up the Q, in other words, the resonant Q, and that's actually set by this pot over here, PQ, appropriate name. And you crank that up, you're going to get a high resonant Q, right? So in other words, the area around resonance is going to have a much steeper ultimate roll, you know, roll off than the ultimate roll off of 6 dB per octave on either side. And you'll get some, you know, boost at that frequency, some gain out of that frequency as well. Okay. Now, if you've seen the video on state variable, you know that you can take the high pass output and the low pass output and run them into a summing amplifier. Gain of 1 for each, and what you'll get out is a notch filter. Now that might seem counterintuitive because after all, if this output passes all the high frequencies and this one passes all the low frequencies, then combining them you would think would give you everything. It kind of does, except for right around the center tuning frequency. And the reason for that is because the high pass and the low pass outputs are 180 degrees out of phase at the tuning frequency. And of course, if you add two signals that are 180 degrees out of phase, they completely cancel. So what you're going to get is a big notch right at that frequency. So all I've done, instead of using a summing amplifier over here, what I've done is I've just taken these two signals and I'm putting in a pot. So the wiper arm is going to move back and forth between the high pass and the low pass outputs. If it's right in the middle, it's like using that summing amplifier. You're going to get a notch. If the wiper arm's way over here, you're going to get a high pass. If it's way over here, you're going to get a low pass. If it's somewhere in between the extremes and not in the center, then you're going to get partial cancellation at a frequency somewhat off of that resonant frequency. So in our case, we have that 1.6 center. If the wiper arm is on this side, right, versus this side, what you're going to see is the notch is going to translate up or down in frequency. So, at one setting, maybe it's going to be 1 kilohertz. You move it a little more, it's going to be 500 hertz. It's going to be, 30 hertz. You move it all the way, and basically the notch goes to DC. You do the other way, it's going to go from 1.6 to 3 to 5 to 10 kilohertz, and eventually it'll be, beyond the range of the op amps. All right, so that's sort of the morph that you're getting. Now, to hook this up into something else, you're probably going to want an output buffer here, right? Otherwise, that impedance is going to mess up the way in which this divides. So you want a high impedance buffer, which wouldn't be hard to do, right? You could just get, an op amp like this. I'm using 081s here, bifed op amps. You could get, for those four, you could get a 084, which is a quad, or a 074, which is a very similar op amp, but slightly lower DC offsets and such. You could get a dual version of that, a TL082 or a TL072, and use one half of that as an output buffer, and then you could use the other half as an input buffer, because here's your input signal. This only sees a 10K ohm resistor for the input impedance. Remember, here on the summer, this is an inverting summing amplifier, so that's a virtual ground. The input impedance that VIN sees is just R1. It's just 10K. So that's way too low for something like a guitar. You're going to want a buffer out there, right? So you can get a quad for this, get a dual for the other two, and you're good to go. Now, let us just do a little AC analysis here. Just do some Bode plots and see what we get. All right, there's a nice sharp notch. I should have verified. Bad teacher. I should have verified the setting on this. So this is at 50-50. Okay. And you can see this notch, and this is going to come in right, like I said, right around 1.6 kilohertz. See how close we can get here. Okay, that's 1.58. Yeah. Okay, so we're there basically within the resolution of the simulation. All right, so that looks good. Now, let's go and change the Q just so you can see what's happening here. So let's crank this from 30 up to, I don't know, 70. All right. And run that again. Okay. You can see that's tightened up a bit. All right, and look at that. Look at that. The bigger this resistor is, the tighter the Q. You could go the other way. All right, we could bring this down to, I don't know, 10%, let's say. Bonk. Okay, you can see how wide that is, right? So here's our original. Here's crank up the Q pot, tighter, and go the other way, and it's getting fatter. All right, let's bring that back to the original value, which I think was 30. If not, it'll be close enough. All right, now let's take a look at the little morph pot over here, okay? So like I said, you move this off the side, and it's no longer a notch. So let's bring this down to like maybe 10%. Okay, so this is pushing way down here towards high pass. Do the same plot. Bonk. Hey, that's pretty interesting, right? So two things. You kind of see the whole high pass effect, right? Here's the high frequencies being passed. Notice gain is 0 dB. We got a little bit of a resonance hump over here because of the Q. It's not a low Q. It's not a crazy high Q, but it's not a low Q. And then this dives down into a notch, right? The notch was up here. Let's go back to the original. Right, so the notch is up here at like 1.6, and now it's been pushed down, and it then kind of recovers partly, almost like a shelving EQ, right? So this, instead of just continuing to fall, it flattens back out. All right, so you got this sharp notch in here, and you can kind of play around with this. I'll just go in here and change the Q again. So crank the Q up to, let's say, I don't know, 80%. And you can see what happens. All right, so you can see that resonant peak really snap up there, right? Here's the original, and we get that resonant peak, which is what we expect with a high Q filter. All right. Let's see, where were we? I think we were at 30, right? Okay, get back to normal. All right, now let's take the morphing guy over here, that pot, and go the other way. So what do you think is going to happen? Well, essentially the same thing, right? As we move this now toward the low pass output, we should see sort of a mirror image of this. And sure enough, right, there's the low frequencies passing, there's the little resonant hump, and we have now translated that notch higher up in frequency. And then again, it flattens out. Well, what happens if we go all the way with this, right? What happens if we bring this up to like 100%? Right, well, it just gives us, what we expect, the low pass output, right? Comes up, resonant peak, and then it just falls down at the expected rate, right? Beauty. Okay, so, that's all well and good. I mean, that's our basic building block for a morphing filter. But let's go beyond this. I mean, this potentiometer right here is what you would have in a foot pedal. So you would be playing your guitar or, your keyboard or whatever the heck it is, and your foot would be going back and forth, which would be moving this between the high pass sort of version, the simple notch, the low pass version, these sort of high pass with notch, low pass with notch kind of things, right? It's morphing between these, right? Back and forth, back and forth. So by itself, that's pretty interesting. But, we can go a step beyond this. I did mention, hey, you could hook up like a VCO to it, right? In other words, a low frequency oscillator, an LFO, in which case we might see something like this. Okay. If this looks totally confusing, check out the videos on voltage-controlled filters. So what we've done, this is essentially the same circuit, except we've taken out the resistor, right? So here's this FR1, our frequency 1, our frequency 2, right? We take these out and replace them. Oops, went the wrong way. And replace them with these OTAs, operational transconductance amplifiers. All right, so they're being programmed down here with a voltage source and a resistance. This creates a current, and that sets up the transconductance. Remember, transconductance is a measure of input voltage versus output current, and that's really what the resistor is doing back here, right? This is taking the voltage from the preceding stage and turning it into a current, which feeds the capacitor. Right? Remember, inverting input on these is virtual ground. So this is essentially doing the same thing, but we can control this transconductance. In other words, how the voltage turns into that current. So that's a programming current in here called IABC, and that is set up by whatever this low frequency oscillator voltage is sitting over our ABC. Still have my little morphing pot out here. So I can leave this pot where it is. See, where is it? Okay, it's down at 10%. And then I can run the LFO, and that'll automatically shift the tuning frequency. So the notch that we had is going to be running up and down in the spectrum. And then while that's happening, you can be stomping on this pedal over here and changing it between the sort of like high pass, low pass versions. All right, so we got an LFO. That's just a simple triangle wave. And let's see, what is this? It's 10 volts. We're running this on 15, so it's not doing a full swing, but it's doing a sizable swing. And it's 500 millihertz, so it's half a hertz. It's 2 cycles per second, basically. All right. All right, now the input signal is a square wave. I want to use a square wave instead of a sine because the square wave has some harmonics in it. 1 volt peak, 220 hertz, so this is the A below middle C. All righty. Okay. So this is nice. I'll be able to do a transient simulation on this, and you can hear the result. And then, unfortunately, I have no way of animating the morph pot, but we can set the morph pot at one extreme, right? So right now, like I said, it's 10%. We can listen to that as the LFO goes back and forth, and then we can move this up to like 90% and rerun it. And again, we can hear the differences between the two. All right. Okay. So let's do that. Do a transient analysis over here. I'm going to run this from 0 to 5 seconds. And we'll just wait. This is, kind of a long sim. I mean, it's got to do, waveform data for 5 seconds worth of output, because otherwise we're not really going to be able to hear the effect. If we only did it for 100 milliseconds, it'll be a bloop and we'll be gone. We won't be able to hear it. So just bear with it. Right? We just have a couple more moments to go. Bonk, there's our output. All right, so open this up a little bit and let's separate out these curves. Okay, so these are all filled in because again, this is 5 seconds and this is 220 hertz. So, this waveform in here is just going, and we're just seeing the envelope. But here is the LFO. And you can see as the LFO is going up and down, you can see how the output waveform is, at least the envelope of it, is changing. All right, so here's the input signal. I'll play this back. All right, that's our basic 220 hertz square wave. Now let's go to this morphed version. All right, so you can hear the motion in there, how it's going like almost like a phaser in a way. Okay, now let's take that, push that off to the side, and I'm going to redo it with a different setting over here on the morph pot. So now it's set at 90, so the wiper arm is way over here. Now we're getting more of the low pass version of this rather than the high pass version that we originally looked at. Now you're going to have to use a little bit of imagination on this to, kind of figure out what's going to be happening as you're playing. The LFO is running back and forth, and then your foot is moving the morphing pedal, right? So you can kind of hopefully imagine what's going to happen because we're going to play the sort of the two extremes of the pedal. Not quite the extremes. I only put them at 10 and 90. But it'll be enough for you to hopefully imagine what it would be like. And of course, you can play around with the pedals. You can play around with the LFO speed, the LFO amplitude, all of those things. Those are all variables for you. Separate the curves out. All right, so again, we see the LFO, the input signal, and here's our output. So before I go any further, this is what we had last time. You can see that the envelope of this, the overall shape of it, is clearly not the same as what we have here. All right. Okay, now let's give this one a listen. All right, that, at least to my ear, says, less high pass. That's a more muted sound. Go back to the other one. So that sounds kind of thin. There's not a lot of bottom end in it. Do it again. All right, so between those two things, you're going to adjust all of that with your foot pedal, basically. And then, like I said, we have the LFO to run up and down and, have some fun. So now the question is, what are you going to use for an LFO? Well, there's lots of options there. You could use, a triangle wave like I'm doing here, a sine wave, sawtooth, so it, kind of runs up slow and then drops, or the exact opposite, runs up really fast and then drops slowly. So I've got some videos on that you can check out, also in the Op Amps playlist under the section on oscillators and frequency generators, waveform generators. So, this is kind of an interesting thing. I would look at this and say, yeah, there's not a lot of maybe application for this when it comes to, instrumentation, like doing signal processing for sensors and stuff. But, electronics is there for us to use. And if it's something that has an artistic potentiality, why not exploit it, right? Okay, think outside the box. I really hate that term. Somebody has to come up with another term for thinking outside the box. Think differently. Be creative. All right, this is Professor Fiore saying, till next time, have a good one. Take care.